So first of all, I'd like to say good morning to everybody now. And today we're gonna expand a little bit what Professor Jean already has been telling us in the first half of our lecture today. So we're gonna be talking about an algorithm called SNC Stream Plus, which is an extending high quality true anytime data stream clustering algorithm. So one more time, my name is Lorenzo, and I'm gonna be talking together with Ricardo. Ricardo, do you wanna say something, even to test your audio?
Anybody hear me?
Yes.
Yeah, it's perfect.
Okay. Okay.
Nice. So to start our talk, one of the first things that I wanted to say, which is awesome in my opinion, is that this algorithm was developed by Professor Jean. I don't know if it was clear to everybody, but this is awesome. And which I don't know if it's right to say, but we made some stalkiation to gather Professor Jean's dissertation, master's dissertation, some conference publishing that he did in the past, and then his latest publishing of this algorithm was in Information System journal. Right. So the way we thought about organizing our presentation today was to start with an introduction about the motivation and the theoretical gap that the professor tried to fill with this new algorithm. Then we're going to talk about the algorithm itself. Both of them, I think Professor just wanted us to talk about the latest version of the algorithm, the SNC Stream Plus, but we also gathered the previous article. So we're gonna show some things that are in the previous article, not just in the final journal version. Then we're gonna show some empirical evaluation. And this is all based mainly on the final journal scheme, like the topics. So the empirical evaluation, we're gonna talk about the algorithm itself metrics and a comparison between the algorithm and the state of the arts until that moment. And then something that I wanted to point out, and I don't know if Professor Jean can say something about it, but in our activity, we proposed something on Kahoot. Ricardo found that Professor Jean made it public, the algorithm in MOA's page, but we tried it very hardly to compile MOA again with the algorithm included, but we couldn't do it. So that's why we end up doing a Kahoot activity.
Okay. Let me just give you a very small comment about this.
Yeah, sure.
I actually have the source code. Okay.
Mm-hmm.
But as you can see, this is something I developed in 2014 and 2015. Okay.
Yeah. Okay. Mm-hmm.
So what happened is that the structure on how many algorithms should be coded inside MOA changed. So I mean, if you get the source code from that moment in the past and you try to compile now, it's not going to compile anymore. Okay. So this is something I really need to get back to and make it available. Okay, so this is why I haven't sent you guys the code, because there is some effort to be put on, okay, to make it happen. So no worries. Okay, I didn't intend you to run any experiments. So Kahoot is totally perfect.
But we tried, that's nice to hear, because we tried very hard to compile MOA back again. So it's kind of nice to hear that even though we tried it, we couldn't do it.
Yeah, no, it's not trivial. Yeah. So don't worry.
Okay.
Yes.
Awesome. Okay. Awesome. So anything else, Ricardo, before we actually start the presentation?
No. Can start.
Okay, so guys, so the first topic, as we said before, is the introduction, and I kind of apologize because we're gonna kind of overview some topics that Professor Jean already talked about. But the first thing that I think it's relevant to talk about is the concept of online and offline steps. And the idea of the online step, as Professor Jean said before, is the algorithm incrementally updates specific data structures, aiming to deal with the evolving nature of data streams and time-space constraints. This is a very important concept, and to represent its instances, as also Professor Jean said, time and memory space restrictions, the feature vector data structure is often used. And then the feature vector is a triple vector, which is compiled of the sum of the objects, the sum of the instances, the squared sum of these same objects, and the number of objects that we have. From the learned feature vectors on the online step, we can make some inferences in the offline step based on some more traditional clustering algorithms such as k-means, dbScan, and some other ones. In the next part here, we try to summarize, very summarized, the way these algorithms work. So I'm not gonna talk about everything again here. The only one that I'm gonna focus a bit more is the last one, which is hasstring, which we understood that it uses one of the previous models, and by returning every possible hierarchy cluster, the algorithm kind of forces the evaluator to define the correct amount of clusters. And this also, in the offline step, it uses hierarchical density-based clustering, which is HDBScan. So that's, I think, the one that I should focus a little bit more, because the other ones were very clear from Professor Gia lecture. Okay, guys. So one of the main things that Professor tried to do with this new algorithm was one of the drawbacks of the offline step, which is based on batch processing. And the ideal case is a data stream clustering algorithm must be able to incrementally update not only its statistical summaries, but also its clusters, thus eliminating the necessity of batch processing upon clustering requests on offline steps. If no batching processing is needed to final clusters, then the clustering algorithm is said to be anytime. And this is part of the reason for the article title, that if I go get a little bit back here, we can see that the name of the article is extending a high quality true anytime data stream clustering algorithm. So that's the idea of the anytime processing algorithm. Now, if Ricardo wants to take on the presentation for now.
Okay, so the SNC stream algorithm is able to satisfy the anytime property when using a social network model based on homophily. You can, the next, please. What is it? Homophily. Homophily is the tendency of individuals to associate and bond with similar others. The presence of homophily has been discovered in a vast array of network studies. Have observed homophily in some form or another, and they established that similarity is associated with connection. Next, please. So the algorithm can incrementally update it according to the arrival of instance from S, but the improvement in this ability to form clusters incrementally using a formation and evolution network model. This network model is based on homophily, where microclusters form clusters naturally during the online step, eliminating the necessity of batch techniques such as k-means and dbScan. Okay, and here we see a flowchart about all the process of SNC stream algorithm. The SNC stream algorithm models this problem as a social network where the set of vertices V represents instance or microclusters depending on the step the algorithm is in. Edges E represent connections between these vertices, and the set W represent the associated distance to the edges in E. Again, subgroups of vertex S is subset of V within the network represents the groups that form the key cluster. Just remember, social network is it's always represented by graph. So this algorithm uses this same um, structure. Basically, this SNC stream algorithm is divided into 3 steps. The first, the initial construction of the network, and then the transformation of the network, and the evolution of the network. These steps are responsible for, respectively, creating a basic network structure and derive initial microclusters, transform the network of instances into a network of microclusters, and evolve the network based on these microclusters. Still, it should be noted that all these steps are in the online step of the algorithm. The initial phase aims to developing a network based on the beginning of the stream. SNC stream starts with an empty network, set G, represent the network, the graph, and 3 sets, V representing the vertices, the set E representing the edges, and the W representing the width and in the edges. Based on an initial window size parameter N, instances xi are retrieved from the data stream S and inserted in the network as vertices. After the transformation of the network as the green area in the flowchart, after the transformation of the network in a microclusters network, the proposal incrementally updates its statistical summaries based on the stream. If an outlier microcluster turns a potential microcluster, it's promoted and the network is rewired. The graph will be rewired. After this, the decay process happens with the microclusters and then is calculated its threshold. The last procedure in SNC stream is the removal of both potential and outlier microclusters. Next, please. Now we show a process to insertion in a network, in a graph. Example, assuming omega equal 2. What's the omega value? Next, please. In this picture, we see the start of the network with one vertex, V1. Okay, the next. In this picture, we have the insertion of the vertex V2, the next one, and then vertex V3. The omega value represents how many vertices close to the new vertex we got to insert new edges. Please, the next one. For example, the vertex V4. It was inserted and it calculates the two vertices closest to him and make edges between them. The next, please. You have to use the process to rewire. how does work? Next one, please. In this picture, you see the same example previous, but the vertex V1, it's in the blue zone. What happened? You can see that with the V4 insertion, V3, it's no more the make a part about the vertex closest the V1. The next, please. In this case, we have to compare the distance in the old neighbor and then the new vertex inserted. And we can see that the distance between V1 and V4 is less than the distance at V1 and V3. In this case, the network is rewired. The next, please. This picture shows the network about the rewiring. Okay? So far, so good. Everybody's hurting me. I'm sorry, I'm a little nervous. Sorry. So far, so good. Okay. Okay. Okay, the next one, please. And now we have an example of network initial construction where two clusters emerge through the rewiring process. Next one, please. First of all, the insertion of the first vertex. Next one, another vertex, another vertex, another vertex. Okay. Repairing this case, the omega is bigger than 2. It's a value greater than 2. About the ruler in that network. Next one, please. The process continues. Next one. Next one. Okay. Can you back to the previous, please? Look at some edges are retired to the next phase. It's because in the rewire process, the degree at the vertices, it will be the same. So when you insert a new vertex, consequently, you have to do some adjusts in the network. Next one, please. The next one. Next one. Next one. Next one. You can see that two areas, one of the top of the bottom, that the quantity of edges between them are each new phase less. The next one, please. Next one. Next one. Next one. Next one. And finally, the next one. And in this point, we have two clusters using the homomorphic concept about the similarity at the instance of each cluster. Okay? So far, so good. Any doubts? Question? No? Okay. Okay, the next one, please. And this case of the K function, we have this formula. The next one. Each core microcluster weight is updated. So each core microcluster weight is updated in this formula. And represent the amount of instances summarized. Delta T is the difference between the current timestamp and the instant of the last update of each core microcluster. Okay? And the lambda is the parameter for the exponential function. Okay? The next one. It's about the next step. The next one, please. The threshold function. In this formula, we calculate the threshold using Ti, that is current timestamp, Tc, that is instant of the creation of outlier microcluster. Tp was calculated at previous process, the window. And lambda is the parameter for the exponential function. And okay, next one, please. And now the algorithm SNC stream plus. The difference, the main difference between SNC stream plus and SNC stream is two differences. The distance memoization, the use of distance memoization, and the rewire trough dissipation. Next one. Memoization, we use the counter pairing function. Imagine that we have to calculate one number with the value of another two. Kind of a hash table. We use a formula that each pair of numbers will generate another number and it will not generate equal values. Okay, so the counter pairing function is responsible, is the one function responsible about it. Okay, next one, please. And this formula is recovering the original values. It's the reverse about the counter pairing formula. Okay, I will give you an example. Next one, please. Suppose that we have a pair that's I equal 3 and J equal 4. And doing the calculation, we got the number 32. Next one. Using this number 32 and using the reverse formula, we got to the original values. I equal 3 and J equal 4. Okay. The next one. With this function, SNC string plus is capable of storing and reusing distance between pairs of vertices of the network, since these are stored in a hash table in this form. It's an ordered pair with the first one is the value of the Cantor formula, and the second one is the distance between the vertices, Vi and Vj. Okay, thus allowing quick distance recovery without the need of recomputations. Since every value present is this hash represent a distance between a pair of vertices in the network, its size is equal to the amount of edges in the network, therefore impacting in an extra memory consumption in the big O, the quantity of vertices to square order. Therefore, whenever an edge removal occurs in the network, its corresponding value is removed from the memorization hash in order to free up memory space. And in the middle of research, we find an article that propose a better formula than the Cantor's formula. And it's a proposal to use less memory that the Cantor uses. It's maybe a future works for who are interested to use in this work. Just we got this interesting to talk to you. Yes, totally. The next one, please. And the second difference between SNC stream plus and SNC stream we use the rewind, but not with all the network. The original rewind procedure performs linear access to all existing vertices in the network, most of times unnecessarily. This occurs since most of vertices in the network are likely to be far from the location of the last inserted vertex, or if it was inserted in a different subnetwork. This algorithm in this the algorithm presents an interactive version for previous rewiring procedure. This algorithm receives as inputs two parameters, the last inserted vertex Vi and the entire network G. The next one, please. So it is the new proposal of rewiring. No? Initially, two structures are initialized. Rewired, a list of already rewired vertices, and to rewire, a queue of vertices that still must perform rewirings. While to rewire, it's different to an empty set, a slight modification to the earlier stated rewiring procedure is performed with the heads of the queue, Vj. Firstly, SNC stream plus verifies if the newly chosen neighbors for Vj differ from its current neighbors. Newly chosen neighbors are defined as the Kj closest neighbors to Vj when assuming a two-hop distance. If the current neighbors differ from the new neighbors, all of the Vj's neighbors, with the exception of Vi and other already rewired vertices, are enqueued for rewired. And the next one. So, SNC stream plus presents decreased average computation complexity with an extra memory consumption bound to O, the quantity of vertices score, when compared to the original SNC stream. Okay, next one. Lorenzo,
So
Agüero.
yeah, so now talking a little bit more about empirical evaluation. So here we're gonna be talking about the empirical evaluation of the algorithm itself, and comparing the algorithm with the state-of-the-art literature based. So the authors made some kind of starting questions about the algorithm parameterization, the parameter sensitivity analysis. So the first parameter that the authors tried to see how it would behave in a matter of the algorithm is the omega, which is the number of connections established, and how omega would impact the clustering quality. The second one was the window size, which is TP, and what's the impact of TP in both clustering quality and processing time. And thus equity decays with the increase of dimensionality D. So these are the questions that the authors made to see, and now we're going to the tests that they made to sort of try to answer these questions. So the first one now in relation to omega. They made a statistical significance test. The name is critical difference from clustering quality. So the CMM here is a metric for comparing clustering quality, and we can see that if omega is assigned with a larger value, the network may become so dense that only one cluster will be found. And oppositely, if omega is assigned a small value, like 1, we can see the network will become sparse and high amounts of clusters. So the only value here that truly have a significant difference is omega equals 1. All of the other values doesn't have like a very large significance difference. And here, still talking about omega and CMM, which is a metric for cluster quality. As we can see the table, there's no single value that we can see that truly has a difference in a matter of clustering quality. So, and then this was run in different experiments. And so, if I'm not mistaken, some of the experiments here are synthetical and other ones are true empirical experiments. I don't know if Professor Gia can tell me if I'm wrong or right, but I think some experiments are synthetical and others are empirical, right?
Yeah, perfect. So all of the RBF ones are those that we played around with MOA earlier today. So RBF stands for radio basis function, which are the round clusters. Okay. So where you see RBF2, RBF5, 20, and 50, this is related to how many features you have. So 2 features, 5 features, and so on.
And this is something that I saw in this table that was not, I think was not stated in the paper. We can see like a little tendency of smaller omegas work better with synthetic data. We can see here the highlights, the bold numbers are maybe a little bit higher on the synthetic data, and we can see the numbers a little bit higher on the experimental data when our omega is higher. I don't know if Professor Gia stated this in the article. I think not, but maybe I'm mistaken. But this is something I think it's interesting to note about the behavior of the algorithm when it's real data and when it's computer generated. So still talking about omega, here we still have both of the synthetical and then also the empirical evaluations. And here is also talking about the performance on the experiments. So the clusters coefficient obtained in networks when varying the parameter omega is now in all experiments when omega equals 1 presents low clustering coefficients in all cases, since the network obtained are not dense enough to form clusters. So I think this is quite trivial, right? if omega talks about the number of connections established and you give us a very low omega, your model literally can't make any connections between instances, so you cannot infer any kind of clusters. And here we can see that just from the update to the value omega of 2, you can see that already all of the tests already jump to a much higher level. So following on, now talking about, and later on the end of this topic here, I'm going to talk about the resume, not the resume, but like the summary of what the authors think is the best combination of omega, the window size, and the dimensionality. Now going to the window size, which is this second question that authors asked to see how the algorithm would behave. So the first one, and we can see that both of the first ones, so the first one is combining some of, no, it's just synthetic data, right? The third one, and then the fourth one that are experimental through the empirical data. So the first one, in all cases, the increase of TP impacts in a clustering quality decrease. The high values of window size allow macroclusters to join the network while they do not respect the actual state of the stream, therefore listening clustering quality. In the second one, overall CPU time used by the algorithm proposed on the follow experiments is higher when you increase the window size. And one thing that I don't know if Professor Gia can clarify a little bit to me, but I didn't understand in the article they said in opposition to what it was expected, CPU time increased with the higher values of window size. I don't know if it's just me, but it seems like if you increase the window size, the CPU time is gonna like maybe increase. I don't know if I didn't understand why he said in opposition to what it was expected.
Yeah, because this window size is not actually like how many instances you're buffering to work with. Okay. The window size is actually how long, I mean, does it take for you to actually check all the weights of your feature vectors and determine if they should be maintained or deleted. So, I mean, we expected, I mean, that larger window sizes would incur in a smaller processing time because we are not spending as much time checking all the weights, right? Yeah. Because when we use TP equal to 1, we are, I mean, after each single instance, we are checking all the weights for all feature vectors. And I mean, what we found is actually the opposite, because if we check it every single instance, we are actually getting rid of poor feature vectors as soon as they fade. So, I mean, this is something that we were not expecting. So using TP equal to 1 was the best option, because when you think about processing time and also CMM, which is what you showed just before, I mean, you get the best results in both terms. So
yeah, it was right at the beginning here, right?
Yep. Yeah.
Nice. And I think something that's, I think, interesting also to notice the difference in behavior when you use the synthetic data and then the true empirical evaluations. I don't know, but here in the second one, we can see that, like, I think it's the electricity, it stays almost like flat. And also this two bottom tests, they stay almost flat. The second one, not so much, but the electricity tests stay almost flat. So as Professor said before, it's also nice to always test on real data stream scenarios, because we may get some very different results. And then the last one here, it relates the TP value with the amount of distance computational performance during experiments. And as we can see here and try to infer visually, distance computations increase exponentially due to the higher amount of microclusters maintained by the algorithm. Now, when we talk about the dimensionality, talking about the distances, we can see in the first graph here the clustering quality, the CMM metric comparisons on different distances using different distance calculations. So we have L1, L2, L3, cosine, and I'm not gonna try to speak that last name, but we have some very different, but they all kind of have the same behavior apart from the L3, which is a frictional distance metric. Also, when we analyze NEMINI, critical difference for CMM comparison on different distances, we can see that the only one that has the highest, like the one that has the highest significance difference is L3. As we can see, it corroborates and it gives a similar intuition as the first graph. So far, so good, guys. So going ahead, the last one talking about the distances is still in the distance metrics. We can see that L3 is the best one for synthetic data and for the empirical evaluation on real data sets. And this is all done with the newer version of the algorithm. Okay, and so yeah. So here, answering all the questions that were established before. So the first question was about the omega, the amount of connections. So no single value outperforms all the other values, with exception of omega 1, which is the worst rank configuration, and omega 4, which presents the best average results. The second question was about the window size in both clustering quality and processing time. So as Professor just said, the best window size that was found was window size equals 1. And it's better than the other ones in both clustering quality and processing time. And the third question was, does ACTI decays with the increase of dimensionality? So with the increase of D, the clustering quality decays, especially with L1 and L2 and cosine distance metrics. We saw that almost all the experiment behaved better with L3 distance. So now going to almost the final part here to talk about the performance of SNC stream plus against literature-based. So the literature-based one were the algorithms that Professor Gia talked to us, teached us on the class today, plus the hash stream. So they compared all these algorithms with the proposed one. So this is very interesting. They made two tables comparing the clustering quality with still the same CMM metric. So the first one, they just used the L3 distance, which was the best one in the alone algorithm tests. They applied the L3 distance just to their algorithm, and they can see that right here in the far right, the proposed algorithm outperformed all the other ones. And then here in the bottom one, they applied the L3 distance to all the algorithms so that they would try to have a better distance metric. And we can see that in general, just visually, we're already having some more dense statistics ahead, but we can see that in average, all the algorithms can improve from the use of L3 distance, but SNC stream still is the best one. And so the far right values here doesn't change because it's still using the same distance metric. So L3 is good for all the clustering algorithms. So the L3 distance metric in all algorithms, we can see here that SNC stream clustering proposed algorithm is the best one in clustering quality. And we can see that it outperforms all the other clustering algorithms with a 95% confidence level. And here, I think one thing that's interesting to say, I think Professor Jean intentionally didn't put S and C stream, the first version, because as he argues in the article, their performance results, like in a matter of clustering quality, are similar, where S and C stream really outperforms the other ones, is in computational expenses, as Ricardo said in the formulation part of the presentation. And here, to kind of illustrate what I'm saying, they compared clustering quality, which the first graph I already showed, CPU time and RAM hours. So in the two bottom figures, we can see that they showed both the new and the older version of the algorithm. And we can see here, the first one, the CPU time. It used to be the one that took most of the CPU time, now is the second best one. Without even mentioning the already talked clustering quality, and talking about RAM hours, now it's the third best one. And so the RAM had quite a little bit of change, but the one that we really see a very big improvement in the CPU time for computation. So guys, now we prepared some questions on Kahoot. I don't know if Ricardo wants to share his screen.
Okay. Just a minute. The link. I'll share my screen. Okay. Everybody can see my screen?
Yeah, it's perfect.
So guys, you know, use these codes.
Okay, so I suppose we should have 7 participants. Is that it? Yeah, 7, 6, 7. Okay,
And just to make it
to go.
Just to make it clear, we were planning to make some more experiments, because when we saw the code in MOA's website, we were almost sure that the experiments would work, but then we had to kind of not improvise, but think about an alternative way. So we kind of apologize to the colleagues because we thought that the experiments would work in MOA. So just to make it clear.
No worries, I should have warned you. I apologize. Yeah,
Okay.
it's not as simple. No worries.
Okay.
Let's start.
Okay, some people thought it was classification. Okay, you got them. Very good.
Okay. Let's continue. Okay. The next one. Okay. The next one.
This is where it starts to get tricky.
Yeah.
Very good.
Okay, most people got it. Nice.
Yes.
Wow, Cristiano is on fire. 4 in a row.
Yes.
Very good. Yeah.
Next one.
This is based on last question that was made that fooled everyone.
Okay, so you actually took it to the next level.
Okay. The next one. Oh.
Well,
Ah.
I'm not sure what to expect from the last talk we'll have because the questions are becoming especially difficult, you know?
Yes, yes.
So, okay,
I
very good.
agree.
They're gonna send a PDF with a lot of formulas, and you're gonna have to send it by the end of the class.
Yeah.
But nobody's lucky.
Okay, let's keep on.
Okay. Okay. Next one. And now the last one. Whoa.
Is it really CPU load?
It's CPU time. It's right. People got it right.
Yeah, it's
I
CPU time.
I think it was on Inside Kahoots just to set the right question, but yes, people got it right. It's CPU time.
Yeah.
Sorry, guys. Sorry.
Okay.
This was just a trick, actually, to see if you guys were paying attention.
Well, I am.
But the champion, the larger difference. Cristiano, congratulations.
Very good, guys. Yeah. I think you have done a very good job because you went beyond the paper. I mean, you did your homework in the sense that you also found out the original paper as well, and also took a look at my dissertation. So I think you deserve a very nice thumbs up for that. So very nice work. So let me just make a very small comment. I think I posted it in the chat, but when you think about the distance computation, it's L dot 3 because it's a
Yes,
fractionary.
L.3.
Yeah, and not L3 because you can also compute L3. Okay.
Okay.
But it's just a small detail. Otherwise, again, very nice work. I think you were able to not only understand but also summarize the paper very well. So good job. I'm not sure if the colleagues have any questions. Is this everything all right?
We're sorry about the time. I got a little faster.
No worries. I mean, one of the main things we're trying to do here in this module is to make sure that you can present things as well. Okay.
Oh, okay.
And I think you guys did amazing. So no worries. I know, Ricardo, you were a little bit nervous, as you mentioned, but I think besides all of the technical stuff we're discussing here, right?
Yes.
I think it's important so that you can realize that you can do a lot of things as well, you know?
Okay.
I mean, most of us, we don't speak English, but if we practice enough and we spend enough time doing it, we can do it, okay?
Yes.
So again, great job, okay? I'm very happy and satisfied with the presentation today, okay?
Thank you so much.
No worries.
Again, I just wanted to say, I think Ricardo spent almost the entire day, and I like stood until like very late trying to compile Java and MOA again, downloading all the source files, but we
Yes.
really couldn't do it. What's the ways so that we can try to use your algorithm, Professor?
Okay, so I think the best thing to do is to go to the GitHub, okay, and then you should download the source for MOA, and then I'm not sure if you have my source code available. I don't think it is, right?
We have maybe a jar file in MOA sites, but that's it.
Yeah.
I think I don't know if it's the source code or.
Yeah, that's why I don't think you should be able to compile it. Because I mean, since I created this in an older version of MOA, I mean, it uses different classes that are different nowadays. So this is why it's not going to run. You actually need the source code. So that's why I'm not, I mean, requesting you guys to run any experiments, okay?
We use
ideally,
the file in this site.
Yeah, that's the one. The problem
Yes.
is, I mean, the other option you could think about, you would need to find the version I used back in the day. So you should see like the MOA from 2014 or maybe 2015, and then try to run with that one. And then it should work. Okay.
And what about Weka, Professor? Does it work on Weka? Because I saw like on the compile line that you call for MOA and then after Weka.
I mean, it's not going to work with Weka, but What we tried to do in the command line was to, also bring all of the things that Weka had. In the case you wanted to run some traditional classifiers in MOA as well. Nowadays, you don't have to do so because when you compile MOA, it's automatically linking the Weka source code. Okay, so you don't have to do it the way we did back in the day. But again, this is actually my fault because I was supposed to have updated the code, but after I finished my master's, I felt like changing the topic I was working on, and then I moved to feature selection. And this actually, this is something that I ended up not working anymore. But I should take some time and update this for sure.
Nice, thank you.
No problem. And again, if you have any issues, if you are trying to run anything and it's not working, just leave me a message. Okay, I'm very keen on helping and figuring out what's going on.
Okay.
Okay, thank you.
Thank you.